Welcome to the last video of section 2. This one is on accuracy and precision, how good your measurements are. So if we're going to start with the accuracy and precision, we should probably define accuracy and precision. Accuracy is how close your data are to the correct answer. Precision is how close your data are to each other. When you look at accuracy, the analogy that is usually used is that of an archery target. The answer you want, or what you desire, is to hit the bullseye. So if your arrow goes into the bullseye, you say that you are very accurate. You hit what you aimed for. If, on the other hand, your arrow goes into, say, the blue, you did not hit what you were aiming for, you would say that this is inaccurate. And each piece of data can be either accurate or inaccurate. Precision is how close your data are to each other. And for this, you do need more than one piece of data. One piece of data does not mean you are precise or imprecise. You need to have more than one. And here you can see that these 4 holes on this target are bunched together nicely. We would say that this is precise, though it may not be in the bullseye. Whereas these 4 holes are not clustered together at all, and we would say that this is imprecise. And precision is usually a measurement of how good your instrumentation is. So there are 3 possibilities. There's high accuracy and high precision, low accuracy and high precision, and low accuracy and low precision. The high accuracy, high precision means you've calibrated your equipment properly and done the experiment properly. Low accuracy and high precision usually means you've done the procedure correctly, but you haven't calibrated your instrumentation properly. And the low accuracy, low precision can actually be due to several factors, but for high school students it tends to be they did not do the lab properly. We do like math and chemistry, and we can calculate how accurate our answer is. This is called percent error. So we need to define some terms. The first is the theoretical value, which is the value you should have gotten. The experimental value is the value you did obtain, and this is frequently an average. The percent error, which is written percent error, is actually a mathematical definition, which is that the percent error equals the experimental value minus the theoretical value divided by the theoretical value. Then you take the absolute value of that number and multiply it by 100. The lower the percent error, the more accurate your data are. So an example, suppose you're asked to determine the density of lead. You weigh out a piece of lead, you measure the volume, you do that 4 times, and you get these values for your density in grams per milliliter. 11.51, 11.47, 11.37, 11.45, all in grams per milliliter. Well, you want to take the average, so you add them up, divide by 4, and you can now say for your samples, average density of lead is 11.45 grams per milliliter. That's what you got. So when you look at these 2 things, your experimental value is 11.45 grams per milliliter. You can go to multiple places to get the theoretical or expected value for the density of lead, and you get 11.34 grams per milliliter. How good is your data? Well, let's take a look at the percent error. We can now plug in what we know and solve for what we don't know. So we plug in the experimental value. We plug the theoretical value into 2 spots. We perform the subtraction in the numerator. This is going to be a positive number, so we can get rid of the absolute value lines. We see that there will be 2 significant figures, 2 sig figs in the numerator, 4 in the denominator. Go with the lesser of the 2. So you get this, which converts to this. And a 0.97% less than 1% error is really, really good. There is a way of determining precision mathematically, but we are not going to get into it this year. But if you're interested, come see me. I'd be happy to tell you about it. So now let's do one example for you to try, and then we can wrap up this video, which wraps up section 2. You're asked to measure the mass of a cinder block, and you decide you're going to weigh it multiple times. As a matter of fact, you weigh it 6 times. These are the values you get. Calculate the average, and you notice that the data is pretty precise. You only vary by 0.08 kilograms between 2.71 at the low, 2.79 at the top. So by the eyeball test, this is pretty precise data. When you get the average, it's 2.75 kilograms, and you tell your supervisor, who then informs you that it should have weighed 3.10 kilograms. So what is the percent error here? Stop, figure it out, come back, and we'll go through it. Go. The answer is 11%. How do we do this? We start with all three things, list what we know. We know that the theoretic value is 3.10. The experimental value is 2.75. Both of those are kilograms, got to have the units. So now just plug the values in. Experimental, theoretical into the two spots, do the numerator math. We see that this will be a negative number, but since we want the absolute value, we shift it to this, and when you do the math, you get 11%. This is moderately accurate. And now you have to come up with a reason as to why your data was different than what it should have been. And given how precise it was, and the fact that you were low, most likely you didn't calibrate the scale correct. So to review, when looking at data, you're interested in the accuracy, how close you are to the correct answer. So if there is a known correct answer for any experiment you do, you will have to do a percent error. Precision is how close data points are to each other. And remember, the percent error is the experimental value minus the theoretical value divided by the theoretical value, the absolute value times 100, and that is note card material. So that finishes section 2. Get all the work done, and we can move on to section 3.